Okay. Now just observe the first graph. Okay. In this first graph, you can see on the y-axis we have temperature, on x-axis we have distance or x. Okay. And this temperature is varying, okay, with respect to x. Only one independent variable, right? With respect to x, temperature is varying. Here we have some temperature. Here it is decreasing, decreasing, decreasing. Up to this point, it is decreasing, again increasing. Okay. So in only one direction, the temperature is higher. Okay. And this is the exact function. Okay. We can define this temperature as a function of x. Okay. And this is the exact function. But let us say if you just collect at different distances, you collect the different temperatures. So let us say at x1 you collected this temperature T1, at x2 you collected temperature T2, and so on. Okay. And now you want to approximate how it is varying. Okay. So there may be some chances that you can simply join like lines. Okay, simply straight lines. If within this point 2 points you can simply join a line here, a line, straight line, straight line, straight line, straight line. You may join simply it as a straight line, or you may join it as a curve. Okay. Straight line has the equation like y is equal to mx plus c, right? Y is equal to mx plus c. M is slope, c is a intercept. So you may either consider it in a linear form. Okay. You may consider it as quadratic or cubic or so on. Okay. So any kind of function you can consider, whatever the suitable. Okay. So what we are doing here, we are dividing this actual function into number of parts or number of elements. So this first part, second part, third part, fourth part, this is all we can call it as elements. Okay. And number of pieces we have divided it into, or we can call it as subdomains. Okay. So you can see this was exact function and this is approximate, right? Now it was for one dimension. Okay. In one dimension or the with respect to x, it was varying. Now here we have u. Okay. On z axis we have u. On here is it is y axis, and here it is x axis. Here it is x axis. Here it is y axis. Okay. Now u is varying with respect to x and y. So what we are getting, this blue part, this is the surface, right? Whenever our function is varying with respect to two dimensions, then we get the function as a surface. Okay. So this we can call it as 2D, two dimension, right? And we are dividing this into small squares. Okay. This square, this square, this all small squares, right? So all what we are doing, we are dividing the surface in the squares. So this is one element, this is one element, this is one other element. So these small parts are called as elements. And these corners, if you are able to see, these are called as nodes. Okay. So this square is called as element, and these corners are called as nodes. So each element is connected with respect to another element by nodes, right? So we are discretizing into number of elements, and that elements are connected by nodes. Now Let us take this example again consider. So here we have divided that into four different elements, four number of elements. Okay, and let us say here we have T1 temperature. Here this is our, if I draw here one straight line, here we have T2 temperature. Now this is first node. Okay, so at this node this is connected to second element. So at this node it will be T2 T2. Okay, so first element is connected to second element at this T2. Okay, second element is connected to third element at T3, third to fourth at T4. Okay, now between T1 and T2 we have straight line. Okay, here in the second part what we are doing, let us say here in the second this part we are dividing this into two different elements, only two elements. Okay, and we are not approximating it as a simple straight line. What we are doing between this we are approximating it as a quadratic function. Okay, so this temperature as is a quadratic. Quadratic is like we have square term, right? So you might have studied quadratic equations like x square minus 4x plus 2 is equal to 0, that kind of. Whenever we have degree as 2, that we call as quadratic. And when we have degree as 3, that we call as cubic. Okay. And this is linear, this is quadratic. Okay. Now, as we go on higher and higher order, like quadratic, cubic, then if you go for fourth order, fifth order, we will be going towards the actual or the analytical solution. If you consider linear, we will have higher error. If you consider quadratic, we will have little lower error. If you consider cubic, again we will have much smaller error, and so on. But it becomes complicated and complicated as we go to higher levels. Okay, so in FEA we generally consider linear and quadratic. Okay, this shape this models we generally consider linear and quadratic. Okay, now whenever we are discretizing or dividing our geometry or domain into subdomain, we may consider linear elements or 1D elements, okay, or 2D elements or 3-dimensional elements. And when to consider one-dimensional element, when to consider 2D elements, when to consider 3-dimensional elements, that all depends on the geometry. Okay, if we have simple axial force and if we have simple rod is subjected to axial force, then we can simply consider it as rod element, right? Now if we have beam and simple beam, like cross section is same throughout, okay, and we have shear force or a movement, in that case we can consider it as a beam element. But if you have, let us say, one plate is there or one cylinder is there and it is subjected to internal pressure, or the plate is subjected to some uniformly varying load, in that case our one dimension, because in rod case we have length and we have area, so this lateral dimension are not that much higher as compared to length, so we consider 1D elements. Okay, but in case of plates, our width and length both are important. Thickness is not that much important, so we consider it as 2D. Okay, and let us okay. Now, if you have some, let us say, very complicated geometry, and in that all the dimensions like thickness, length, or width, all the dimensions are important. Like one is not negligible or one is not small. In that case, we have to consider the solid elements. Okay, and the solid elements may be tetrahedral, rectangular prism. There are different number of solid elements. Okay, we can consider it. But when to consider it? Whenever our geometry is complicated and we have all the dimensions important. Like we cannot assume that our thickness is much smaller as compared to length and width or something like that. All thickness, length, width are important. In that case, we can go with the solid elements. If our thickness is smaller, okay, as compared to our length and width, then we can go for 2D elements. And if our only length is very much high as compared to width and thickness, then we can go for 1D elements. Okay, I think this is clear to you. In first example, in this example, this is tower. Okay, and in that tower we have replaced each component by 1D element. Okay, so each component we have simply replaced like 1, 2, 3, 4. So we have replaced each component by simple 1D element. In second example, here this is 2D because here length or both the dimensions are important. Perpendicular plane is maybe thickness that we have neglected. And if you see the third case, so the geometry is very much complex, right? And here we cannot assume that thickness is very much small as compared to width and length. So in that case, we have solid elements in this case, right? Here it is 2D, here it is 1D. Now, what are the basic steps in the finite element method? So first we will discretize, right? Domain discretization. Then we will select element type. Okay, what element we have to use. Okay, and in that also whether to go with the linear or the quadratic. Okay, the second step. Then we will have the uh, stiffness matrix or the property matrix. Okay, then we will assemble the stiffness matrix. Okay, now if you know the F is equal to K into X, this is the equation for the spring, right? Force is equal to K into X, where K is spring constant, right? We have the similar equation. K is our stiffness matrix. There it was spring stiffness. Here it is element stiffness and then global stiffness. Okay. U is our degrees of freedom, like displacement or the rotation. F is the load factor. Okay, or the nodal force vector. This K is stiffness or the property matrix. Okay, we are representing it in the form of matrix, not just a simple equation. And this U is the nodal displacement vector. Nodal displacement is like at each and every node we have some displacement. Okay, so that's why nodal displacement vector. This is nodal force vector. Now Next step, in the next step, once we have assembled the stiffness matrix and we have written the equation, then what we will do, we want to solve it, right? But before solving it, we should have some boundary conditions, right? We will have some boundary conditions. At some points, we will have something known to us, okay? That are our boundary condition, boundary and initial condition. So first we will incorporate our boundary and initial condition in this equation. Then once we have put our boundary and initial conditions, we will try to solve this equation to find the unknowns, right? And what are the unknowns? Uh, that may be our displacement or the rotations, okay? And once we have the this u, whatever the unknowns we have found, then we will try to find, let us say, strains from the displacement, then stresses from it. Once we have displacement and strains, we will try to find stresses, right? And once we have stress values, once we have strain values, we can compare it with respect to allowables. That is for like our structural analysis. And for thermal analysis, what it may be, we might have to find, may want to find the temperatures at different locations. And sometimes we might have to find the gradient at temperature gradient at some location. That may be unknown. Okay. So depends on the problem. Okay. So basic steps are clear, right? Now we are not finding the exact solution, right? We are approximating. So there will be errors. And what where from the errors may come? Like we have different steps, and each step there may be some error. Okay. So there the while considering the domain itself, we may have some errors or the some approximation. That's where there may be some errors. Now, while considering element and the interpolation function, we may have some errors, right? Because we are approximating either it as a linear or quadratic or cubic. So we are approximating, right? So we are not taking exact. So there may be some error. Now, while combining it or integrating it, we may have some errors. Okay. Now, once we have solved, once we have everything, there may be computer errors to consider, like rounding off. If you have some, let us say, fail point 5, 7, 8, 9, 4, 4, something like this. So what we will do, we will approximate to the significant digits. Okay, let us say 12.57. Okay, so there is round of error. Okay, so these errors may be there. And how we can measure the accuracy with the help of error, exact solution minus APM solution. Okay, so the error will depend upon the number of elements. Okay, the order, approximation order as well. Okay, now just consider this example. Okay, we have plate and we have hole at the center, and we want to discretize it. Now in first case, we have discretized it with the triangular elements. Okay, here. And if you see here at the center, we have like this circle. It was like, it has how many sides? 1, 2, 3, 4, 5, 6, 7, 8, or 7. Okay, sorry, 8. So we have approximate it circle as octagon, right? Now in the second case, we have decreased the element size. Here, if the element size was higher. Now in the second case, we have decreased the element size. As we have decreased the element size, this this looks like more like a circle. Okay, actual circle. So as we go on decreasing this side, it will be close to the circle, right? But there, here we have 220 elements, here we have 912 elements. So as we go on decreasing the element size, we will have more and more number of elements, and if you have more and more number of elements, it will take higher and higher time to solve the problem, right? So we have to optimize the element size so that the solution time is less, and we are having lower error. So both things we have to consider. So I think this is fine for this lecture, and we can continue in the next lecture from here itself. If you have any doubt,